Okay, dear student, let us see what is there in this question. A girl looks at a flat vertical glass window on an automobile. The window has a thin transparent coating. White light from the source is reflected to the girl from the coating and from the window. Okay, so this white light is coming. White light specifically means that it would be having all the wavelengths in the visible range, ranging from red to violet. Now, all the colors are falling on this coating and they are getting reflected back. And so, when they're getting reflected after that, the girl is able to see the light which is coming. Outline why the light reflected to the girl has one wavelength missing. Okay, so one thing is sure, that when the light will be going through the coating, what happens is there are two reflections which are taking place. The first reflection will be taking place from the thin coating which is shown in the diagram. The second one will be like this, isn't it? Like that light will also go towards the eye of the girl. So what is happening when these two lights are traveling, both of them are undergoing destructive interferences and constructive interferences at various angles. So when it says that there is one wavelength which is missing, it only means that for one particular wavelength, it could be anything, but whatever it will be, there is a chance that it will be going for the destructive interference. Yes, there will be some other wavelength which would be undergoing constructive interference, but in this case, they are asking about the missing wavelength. So clearly, we have to say that one wavelength out of the complete band, somewhere will be some particular value of wavelength will be there which will be undergoing destructive interference. That will be the answer for the part A, and we can clearly see the mark scheme here. Let's see. There is partial reflection at the front surface of the layer and also at the glass layer interface. Destructive interference between these reflections occurs at the missing wavelength, like whatever it is. So even they're talking about the destructive interference. Now this we already know that whenever you have this kind of a diagram and they talk about a coating there, they are really referring to the thin film interference, and either the constructive interference will be considered or the destructive interference will be considered there. So one out of these two will be there. So either they will say that we want reflection to be maximum, so constructive interference will be taken place, and if we say that we want this reflection to be minimum, like minimize, so if we want to reduce that, then destructive interference will be taking place. That's it. Formulas we would be discussing now in the next part. Okay. Let us go to the next part now. The refractive index of the coating is 1.63 and the refractive index of the glass is 1.52. The thickness of the coating is given. Determine the wavelength that is missing. So now we want to find the wavelength which is missing. Assuming that light is incident normally on the window. Yeah, of course, definitely. Let me explain you what is happening now. This is very, very important. Okay, I tell you. First of all, the topic here is thin film interference. Thin film interference, you must be knowing the formulas. The formulas are already given in the data booklet, but the formula given there are like they can create a bit of confusion here. Let me tell you. So thin film interference is when there is this film here. It's like this. So this is the glass material, this is the film material. Okay, and the light is falling like this. So what happens is, like, this light goes like this, and there is some light which is entering into it, getting refracted, then getting reflected, and then it is able to pass through the medium. So basically this radiation which I'm calling as 1 and this radiation which is 2, they are undergoing interference. So some angles would be having destructive interference and some angles will be having constructive interference. So different kind of things will be there. Now, it could happen even if this angle is not 90 degree, like this angle is given, and this angle is, of course, not zero. This angle is not zero. But in our books, in our syllabus for the IB, this angle is taken to be 0 degrees. Now, that is written here, the incident light is normal to the window. Normal means that the diagram is shown like this. There is this theta that we have shown in the diagram here, but actually it is not there. This angle is shown only for understanding purpose. So what is actually happening? Light is coming like this, 90 degree, it goes like this, it goes like this. So every light is actually overlapping each other. Because of that, creating diagram is, it becomes very difficult, and obviously the student will not be able to understand what is happening because it is completely overlapping each other. That is why we just write it that okay, the normal is incident, but in the diagram we do not show it to be normal. Got it? So this angle, according to the question, is 0 degree, but according to the diagram, it is not. And in the diagram, we will not show it as zero, but we will assume it as zero. Anyways, now what happens after this? There are two cases now. Even this is a very dicey part of this topic because they are not dealt with either in the book or in the data booklet. It is not specified. So I will be very specific here. Now, what happens? Case number one is when this is a rarer medium, this is denser, and glass is again rarer comparative to medium. Like for example, in this case, the refractive index of the coating is 1.63 and the refractive index of glass is 1.52. Clearly, this is rarer, this is a denser, and this is air. For air, the refractive index is 1.0. This is again rare. So I am naming this as RDR. RDR means rare, denser, rare. Everything is from the point of view of coating. Okay, so rare, dense, rare. If this kind of phenomena is taking place, then these formulas are valid. So we will say that the path difference, um, 2 and d, yeah, 2, this refractive index is n, and I'm using the word t. T is the thickness. 2 and t is equal to, now for constructive interference, this will be using the formula n plus half into lambda. Now, if you open the data booklet and you see, this is the formula that is given. Instead of T, they are written D. They take D as that, but I do not assume it to be D because there are many D's now. That is why I take T as the thickness. It is T. So 2NT, where this N is the refractive index. By the way, we could have used some other variable here also, but the data booklet is choosing this as M. So M is a integer, and M, it can be equal to 0, 1, 2, 3, like that. So our minimum value for this will be M is equal to 0 and things will be valid. They will be good to go. So M is equal to 0 we will be doing. So this is 2NT into this. And for destructive interference, it is going to be 2NT is equal to M lambda. That is destructive interference. And again, M can have the value of 0 also, but we will not be taking 0 because otherwise everything will become 0. So we are not going to take 0, but although it is 0, 1, 2, 3, like that, so we would be going with 1. Okay, so this is what we have to do. And in this question, this is typically, it is going for case number 1, but there is case number 2 also, and there will be many questions those who are using case 2. So I would be discussing case 2 also here. And um, let us first solve this question and then I will tell you what is case 2. So we want to be this interference to be destructive because we are working for the missing wavelength. Clearly 2 n t should be equal to n lambda. This is m lambda. M will be taken as 1. So 2, refractive index is 1.63. Thickness we want to find, and the thickness is given 1.43 nanometer. And that will be equal to wavelength because m value is taken as 1. So this we have to find, and our answer will be 2 into 1.63 into 1.43, 4.66. So my answer is coming out to be 4.66 nanometers. This is the wavelength that will be missing when you are watching that. Okay, let me see what is the answer given. 4.66 nanometer. 4.66 nanometers. The answer is 470. I think there is some problem with the zeros, probably. The answer is in nanometer. Just a moment. Let us verify. There must be some error. Some calculation mistake is going on. T is given as the thickness of the coating is this. Refractivity is 1.63. Okay, my mistake. I've chosen it to be 1.43 by mistake. It is 143. So, anyways, so we remove this decimal. It means like we are going to kind of multiply by 100, isn't it? So that will become 466 here. Yes. So the answer given is 470, and this is how we do it. 470. Why 470 is the answer that is given here? Because usually they round it off to two significant figures. So accordingly, we can do that. So 466 nanometer is our answer. Now I'm going for the case number two. Please be serious now. Let me tell you what is happening. I think this should be clear. I'm erasing this part. Yes. Now you see, there is case number two now. What is that? Now, case two is somewhat like this. Let us say the refractive index of this is not 1.5, it is 2. It is 2.0. Now, in this case, the refractive index here is not rarer. So this should be rarer, but it is not rarer with respect to the coating. So this becomes rarer and then denser and then denser. So according to the for this, it is denser here. That is why I'm using RDD. See, these are my code words. They are not written in any book. So you can create your own code words. That is not a problem. RDD means this is rare, this is denser, and then this is again denser. So this is not rarer now. This is denser. It is RDD. So this is two. In the case of denser medium, like the glass is denser, there was a question that said that a solar cell is having a refractive index which is more than coating. What to do in that kind of case? In that kind of case, these formulas are swapped. So what is happening in constructive interference? In constructive interference, 2 and t, it becomes equal to m lambda, and in destructive interference, this becomes m plus half into wavelength lambda. So destructive interference, it becomes m plus half lambda, and constructive interference, it becomes this. So they are basically swapped with each other because of the phase differences and all that. So that is it. This is it. This is how we do it. And this is the case number two. This question is from the case number one, but there are many questions that IB has asked. They are belonging to case number two. Now, ironically, this thing, just a moment. Ironically, case one is given in the data booklet in interference in I think 9.4, 9.3 something. These formulas are given, but they are not discussing case two anywhere. So that is the problem. So students usually see that, okay, this is the thin film interference, so the formula is given in the data booklet. They just apply that without thinking, and that is why there are errors and they do not get the correct answer. So this is the problem, and this is how we do this. So this is case number one. Anyways, this is how we do it. Let us now move to next question. B is done. Let us go to C. The automobile is driven directly away from the girl at a steady speed of 15 meter per second. So there is the automobile here, and it is driven away from the girl. So this is the girl, and it is driven away like this. Is driven directly away from the girl. Musical note is emitted by the loudspeaker in the automobile. The frequency of the musical note heard by the girl is this. So actually the frequency is F, but here the frequency which is recorded is F dash. And the recorded frequency is 410 hertz. Outline why the driver of the automobile and the girl hear different frequencies from the musical note. So it just kind of outline why. So in this case, we are just going to tell like, okay, fine, Doppler effect is taking place, and we are going to explain it accordingly. That because the vehicle is going away, it means the gap between the two waves will increase. And that is why we can say that the wavelength is now bigger, and so frequency will be lesser. So the frequency which is heard by the girl will be lesser than the original frequency. That is what this is what we are going to write here. That will be the explanation. We will see the mark scheme later. Let us first go to the question. The speed of the sound in the air is 330. Calculate the frequency of the musical note emitted by the loudspeaker. So this is the frequency that we actually want to find, provided that the speed of the sound is 330. So this question is from Doppler effect. Now again, for the Doppler's effect also, I am having my own method to do it, and you have to listen to this method properly if you have not watched videos in the online course. Or you can watch the video and then you will be everything will be clear. So what I do is I will first draw the direction of the sound. So the sound is traveling in this direction, and the speed of sound is v. So the velocity with which the source is traveling, this will be taken as vs, and this is the observer. So the velocity of observer is zero because observer is not moving. So what I do is, according to my method, I only remember one single formula, and that one single formula is this. Sorry, that is this. The only formula, one single formula, which is applicable in all the cases. Usually what people do is, and usually what is given in the book is, they give you each formula for like each case. So like it's kind of 5 cases or 6 cases, they will give you 6 formulas. Obviously the students are confused and they don't know what to do. But what I do is I give you only one single formula. You have to remember this formula. No plus, nothing. It is only minus here. And along with this, we are going to use one sign convention. Now, what is this sign convention? The direction in which sound is traveling is taken as positive. It means this direction is positive. It means left direction will be taken positive and right direction will be taken as negative. Sign convention is all set with the help of the direction of the sound. Obviously, the direction of the sound will be from source to the observer. Obviously, like you see, that sound is also going in this direction also. But we are not considering this because our observer is on the other side. So this is positive. All other directions, they are taken negative. So this is positive. This is taken as negative. Now we are going to substitute the value. So this value is 410. This we do not know. Velocity of sound is 330. Velocity of observer is 0. Velocity of sound is 330, which we are taking positive. Okay. Now velocity of source is negative. So it is negative 15. Simple and straightforward application. Plug in the values, get the answer, and your answer here will be, this is 330 plus 15, that will become 345. And so F is going to come out to be 410, 345 divided by 330. So our answer is 428.63 hertz. Well, the answer is this, but if you want to reduce it into two significant figures and all that, then the answer given should be 430 hertz. But let us see what is the answer given by IB. So by calculator, the answer is 428. And now I don't know if they would be doing that kind of very high approximation or not. Let's see. 430. Yes, I told you they would be doing it. So they have done it. So our answer is 428.63. So if we round it off, though that should be rounded off to 429, by the way. But anyways, they are usually, I have seen it, IB is interested only in two significant figures. So every time they round off to two significant figures. Okay, and the reason for that could be that the velocity is given here, like 15 is the velocity. So 15 is having two significant figures. So the minimum significant figure is 2. So your answer will be two significant figures. That is why they report it to be 430 hertz. And this is how we do this. I hope that with this question, you would be able to understand what is happening in the Doppler's effect also. The formula and the method that I have given you is valid for each and every case. It's not context sensitive. It is for each and every case. Just use the sign convention properly, plug in the value and get the answer. Let's see if there is any other question that we have to do. Okay, that's it. So this is where the question ends. Thanks for joining and thanks for watching the video. Please share the video with all your friends. See you in the next video. All the best. Bye.